So Lorenzo, can we start the game?
Yeah, perfect. Okay, you share the screen.
Lorenzo, there was a question in the chat. The
Yeah.
question is, what about the environmental cost of cloud computing versus edge computing?
Well, I mean, it's not the same cost. I mean, the approach is of course the same, but the resources that are provided are not the same resources. So of course, cloud can provide some powerful resource, and of course, I mean, the cloud providers typically I mean, asks more, I mean, in terms of payment. While edge computing, I mean, of course, it's something that it's a bit cheap. But this is, I mean, related with the resources. So at the end of the day, in an economy of scale, and if you think, I mean, the projection of the possibility to have eight virtual CPUs that are, I mean, just two virtual CPUs in an edge device, and this is more or less, I mean, natural that the things goes in this way. But I mean, the model is the same. It's pay per use, so it's utility computing, like it is utility for the gas or for the electricity. So the model that the cloud community uses, it's still the same. Okay. Okay, so let me introduce at this point the concept of microservices, which is really important for discussing about containers. And I mean, just as already introduced, I mean, what I mean, the community did is moving from the monolithic development approach, so building a single stack of application that is typically long-lived and deployed to a single server. Well, today we have applications that are constantly developed. They are built, I mean, in loosely coupled components. New versions are often deployed, and they are deployed on a multitude of services. The benefit of the monolithic was that it was simple to test, develop, deploy, scale. Let's think about this image here. So there is a browser which is in our client with an HTTP connections that downloads an HTML, or a client application. So could be a desktop application or a mobile one with some REST JSON API that is used. Then there is one single block of applications inside. The storefront UI module could be just a set of classes in our object-oriented programming, which is inside the monolith. The catalog module could be again another set of classes which are that are inside the application, and again for the reviewers, the order. It's easy to scale the whole application, because if you need more resources, we have just to ask resources for the entire application. And this is easy to deploy, really, because we have just one single application to deploy, where there inside there are different sources, so um, different solutions. But it's really difficult to maintain, because if one component fails, so if the reviews module fails, then also the catalog will fall down. Because if the review modules will crash, the entire application will crash. Because if there is an exception, for instance, just to discuss practically um, into the review module, then the entire application will crash if the exception is not managed. That means the service will not be available for some moment, will be discontinued, and of course will take also a long time to restart, because all the components needs to be restarted. Think also about the update of the orders module. It needs to update the entire monolith. So that means that the entire application needs to be switched off and switched on again with the new software. Of course, I mean, this cannot be the cloud computing model. So that's why, I mean, large companies like Amazon, eBay, Netflix, Google, Microsoft, they mean adopted the microservice architecture. The microservice architecture is an approach where the software, the application is built in with a small size. Any application is specialized, so does one single thing, and is tightly coupled with other services. So the review, of course, cannot exist without the order, because typically we do the order and then we do the review, but they are built like two different applications, and then they are coupled with some REST API, for instance. So each service can run its own process, can be written also with different programming language, something that is not so easy in this kind of approach. Is platform agnostic because I can deploy it on a Linux system or in a Microsoft system, and this is the same. And is independently deployable and replaceable. This is the same architecture, but in a microservice way. We have still the browser, we have still the mobile device with HTML, HTTP, RESTful, JSON, and so on. We have an API gateway which collects everything like a queue of requests, and each of the services inside this e-commerce example are different applications. The catalog service is one application with its own catalog database. The review service is another application. The order service, the any kind of service that could be built by this e-commerce. So each microservice is then designed to address one single application aspect, and has, I mean, functions, logging, data sets that are, I mean, confined, bordered inside that specific application. I mean, the microservices are, of course, much more lightweight than a monolith, and they uses, of course, APIs in order to be in touch with the other services. As you can see, if the review services needs to get some information from the other services, this is not done directly from the review service to the order service, but this is done by this API gateway. So there is like a element in the middle that tries to collect all the requests and sort the request to the right destination. So the concept of API here is really strong, it's really important. So it's a way for the software components to talk with each other. Any service can create a RESTful server, but at the same time could be a RESTful client for receiving requests and for making requests. So the API, at the end of the day, allows the communication between any software inside the microservice application. Browser, for instance, have API. That's why, I mean, API is one of the tools that typically is used inside the microservice architecture. So JavaScript runs API, but Python, Java, all the languages, I mean, can help us to create API. So at the end, API commonly allow two services to communicate. So the web service or the web API is an API that allows the application to communicate with each other. All the web services are APIs, but not all the APIs are web services. Okay, so this is an important difference in this aspect. So we can have a smartphone with PHP. We can have a desktop computer or a tablet with a C application. We can have, I mean, different devices with different application. All of them uses the same standard, which is the API, to communicate with the web service. So typically we do it with the RESTful. RESTful is it's not a technology, but it's a set of rules that specify the best practice in order to make the communication. This is based on the client server model. It uses URI and the URL, so the uniform interface. It's stateless. If we want some state, we need to make some cache. That's why the rest is cacheable. And it's a layered system. Typically, we have different methods that are also took from the HTTP. We make some posts to create objects on the web service. We have the put to update this object in the web service, to have the get to just get the object from the web service, or the delete to remove this object from the web service. So these are the four most common methods that RESTful allows to use. And with those, we are able to communicate and to manipulate objects all around the microservice architecture. So the client server takes advantage from this. So both the client and the server are completely autonomous. Okay, of course, it's the client that makes a request to the server to manipulate some object which is in the server. So it uses HTTP, so makes an HTTP request using the API, and receives back the HTTP response, which will be in some data format, XML or JSON. Today it's really common also to use YAML, or could be also an HTML page, or an image, a document. Okay, so in this way, the two ends, the client and the server, can easily communicate. So the API operates on resources that are represented by URLs. So when I talk about an object, the object is reachable or modifiable because the object is identified inside the web service as an URL. The URL can, it's the domain, the address that typically we have in our address bar in the browser. And if you try to open, for instance, an image in a new window, you see the URL also with the name of the image, so with .png, .jpeg. So that is the specific address for that object. So with the URL, we can manipulate data between the client and the server. So as I say, the server is stateless. So each request from the client and the server should contain, all the information needed to maintain, alive the communication and to be reliable. Stateless communication has several advantages because, like this, the RESTful design could be scalable because the server doesn't need to maintain, the state of all the clients and all the requests of the clients. Consider that this kind of requests could become really a lot. Let's think about an e-commerce Amazon when there is the Prime Day, for instance. They experience a lot of requests in the day. If they had also to maintain the state, they could consume much more memory. Then the robustness. So the stateless requests minimize the impact of server failure on client. If an application fails, then we have to restore all the states. This could be complex, to manage. That's why, it's good that REST API are stateless. And then this is efficiency. So by avoiding resource-consuming state management, the stateless communication lead to a more efficient approach. Again, stateless could be modified in a state approach if we use cache. Cache, we commonly know it's used for collecting data from the utilization of some web page or some web object. So cache is typically used, in terms also of facilitating the communication. So making quite quick the download of new data that are asked more frequently. They are put in cache, and then we can access directly them from the cache and not from the server. And typically, the cache server is deployed next to the client. And then we have layered systems. So This allows to separate the architecture into layers, such as user interface, business logic, data access. So each of the layer can include one or more microservices, one or more modules. So we have an improved cacheability like this, enhanced security, and better manageability. Okay. With RESTful web service, I mean, it commonly uses JSON as a response. Commonly, it uses HTTPS as application control, and they are commonly referred as the REST API, REST Web API, REST Web Service. This is a JSON example. It's something that today is really common to see. It's called a JavaScript object connection. Is just to make an analogy with Python, is like a dictionary. So we open and close the curly brackets, and inside we have a key and some value. In this case, is a key with a list of other dictionaries. Inside we have the key value, other ID1, and the title, What a Great Hotel. So this is like a review for the hotel. This is also like some database today is built, like MongoDB, that uses JSON documents. Okay, I mean, about this I already explained. So the get in the RESTful is used to get an object from the server. The post is used to create an object in the server. The put is used to update an object in the server, and then we have the delete to remove an object in the server. Clearly, all these HTTP methods needs to be secure. We do it with the toggle, with the two-factor authentication. But I mean, this is how does it work. Microservices, I mean, were really the winning approach for making lightweight virtualization. We saw in the first module that the traditional virtualization machine is something like the one we have on the left. We have an infrastructure, we have the hypervisor. The hypervisor emulates the underlying hardware, so creates a new virtual CPU, a new virtual memory, a new virtual disk, a new virtual network, and then there is a guest operating system on top. This could be a Linux one, this could be a Windows one, this could be a Mac one, and inside we have multiple applications. Application for Linux, Windows, or Mac. These are silos, so virtual machine cannot interfere with other virtual machine, but this is not lightweight. Why? Because we have to re-emulate the underlying hardware. Container is something much lightweight to use. As you can see, we have still the infrastructure, of course, we have the hardware. We have the host operating system, so the operating system that we use, like I have a Linux one. Then we have the Docker engine. The Docker engine is one of the container engine, okay, because there are most of them. One of the container engine that tries to negotiate the use of the underlying hardware for all the containers. Application A, application B, application C, and so on, all of them are containers. And considering that they are microservices, they are really specialized. That's why application A is only application A. There is not application A and also B inside a container. Otherwise, we violate the microservice architecture. So this is lightweight. We don't emulate again the underlying hardware, but the Docker engine negotiates the utilization of the resources. Microsoft, the microservice architecture helps to, scaling the utilization of microservices. So we could have multiple versions of the same service deployed. The service one, for instance, here is deployed 3 times because, the service one is overloaded in terms of request. So that's why, at the end of the day, it's better to deploy it more. Something that with the monolithic architecture we cannot do. The load balancer will help to move the computation from one microservice to the other. About elasticity. Elasticity in a monolith means increasing that resource, CPU, memory, or disk for the entire monolith. But for the microservice, we can do only for the service that we need. And then, I mean, we can have a high availability of this microservice. Just because, I mean, the microservice could be available in multiple replicas. And that means, I mean, the application is always available, okay? So when we understand that the application needs more resources, we can also replicate. So that means we can have an horizontal scaling, replicating the service, or a vertical scaling, increasing the amount of resources, increasing or also decreasing, okay? Because if after the computation we don't need to use so much resources, then we can decrease them. And then, of course, the robustness, as we said, because in a monolith, I mean, we have an hardware failure that for one single application inside the monolith will crash the entire application. For the microservice, only that microservice will crash. I mean, typically the microservice system, as I mentioned before, uses a common approach for the communication. In the image we saw before was the API gateway. More generally, is a data or event bus that generates, I mean, the communication and the events between the service. Well, when we should use the microservice, typically when the complexity, I mean, of the application grows, and at that point, I mean, we want to manage them much easily, maintaining anyway a good level of productivity of that application. Microservice then are used like this. So we can have multiple microservices that implement different applications. These different applications could be done with different programming languages. Each of these applications could have its own database. So for instance, the microservice one is a container with an ASP.NET Core, has a CRUD design, so RESTful for create, read, update, and delete, and uses a SQL Server database. We could have then a microservice 6, which does something similar with the Node.js, and so on. Microservice 8 with Java and other kind of. This is then the example for the e-commerce. In this case, I mean, we have identity microservice. It's one microservice, the catalog microservice, the ordering microservice, basket one, marketing, and so on. Each of them is a different microservice, and the event bus is used for the communication. Okay, of course, each of them has different APIs. And the major, I mean, microservice design concern anyway are to identify microservices and microservice components, understanding well how the microservice needs to communicate, making security between the microservice because there is much more network traffic between the microservice, making the management resilience and transparent, and having, I mean, upgrades that doesn't have any downtime. Let me now move to the Docker. Let me now move to Docker at this point. And to see, I mean, and so on, I will show you again some command. As I said, you will see some command in the session in the afternoon. But I mean, some command in action in the session in the afternoon. But now I will show you something about the slides. Read a comment. I mean, they could be available. Professor Peters and the organization, of course. Docker. Why Docker? Docker is the engine that we use to create containers. So we have the infrastructure, we have the operating system. Inside the operating system, we install Docker, and with Docker, we create containers. So Docker, at the end of the day, is a tool. It's a tool for creating, deploying, and running applications inside containers. A container is a software package that contains, the entire software inside and everything that is needed to this application. What I mean, anything, everything, also the dependencies. Of course, when I create an application, this application has dependencies. I install all the dependencies inside and then the application on top. So, of course, and also the settings and the configuration that are needed. So containers are similar, as we have seen, to virtual machine, but they are more lightweight. They don't need an hypervisor like to negotiate, with the operating system. They don't need to recreate the virtualized hardware. This is again, the picture, so I don't replay the explanation of this, but just to be clear that we don't have the hypervisor, that's why it's much more lightweight. Docker is running like a daemon process, okay? This is called Docker D. And Docker inside has REST APIs, and with the REST APIs we use the functionalities of Docker. Typically, we do it with the command line interface, so the CLI, using the Docker command. There is also a Docker desktop application with a user interface. With a Docker desktop, we can typically pause or run a container. We can remove a container. We can read some log from the container. And sometimes we can also open a shell inside that container. So the Docker desktop, is a solution that could be useful, and more user-friendly for using Docker. So the Docker daemon is like the server of the engine. All around the Docker daemon there are REST APIs. As I say, then there are the Docker client to use the REST API, and all around there are different applications inside Docker that allow to manage the network, to virtualize network, to virtualize the volumes. Volumes is about the storage. To create and manipulate images. So the image is like a template of a specific application, and then the container itself, which is the final result. So the element that we run and that runs also our application. So the creation of a Docker container starts from an image. A Docker image is a template, as I said, is a read-only template, contains a set of instructions. Of course, we can create our own image. For creating, and we use, this image, so this set of instructions for create a container that runs on the Docker platform. Here in the bottom, there is an example of Docker image, which is online available, is the MySQL one. So this one, installs the most common relational database management system, which is of course MySQL. Docker is built, is created like this. We have in the client the three most common commands. There are more commands, of course, but the one for building that builds the image, and after the building, the image can be run. But before building, we need to pull the image. So like, we pull some source code from a repository, we pull the image from the Docker container repository. In the Docker host, which is, what we have in the Docker engine, we have the Docker daemon. This helps to communicate between the different elements of Docker. So the images is an image of Ubuntu, is an image of Nginx, for instance, or Redis, and then this image becomes a container. On the right, we have the registry. The registry, as I said, is the repository where we have a template of images that are already ready. The registry could be a public one available on online, or we can create, our organization can create its own. So how to install Docker, is available in these links, so you can then install it for testing later, both for Windows, Linux, and Mac. But anyway, on the Docker website, there is everything. With these lines of code, we can simulate the installation on Ubuntu operating system. So we install the dependencies that are needed to install Docker. Then Docker is installed. I mean, the official GPG key in Ubuntu is added with this core, and then Docker is installed, downloading the package from the Ubuntu. And then at the end we can install the Docker clip. Another tool that is really important we will see is the Docker Compose, and with this Docker Compose, I mean, we can run multiple containers at the same time. After the installation, the Docker run hello world will, I mean, it's like the hello world for containers, will show up this message, I mean, explaining what is also the architecture that we have, and we know that Docker is running in our system. Typically, I mean, how do we run how do we utilize an Ubuntu operating system inside a container? We typically do creating a container with the run command. So the run command, Docker run -it allows to have the Ubuntu operating system in a interactive way. Okay, the alternative is to have it detached. Detached means it's running in background. Of course, we cannot interact with this. So the only way to understanding if something is going good is having logs that are written in some file. This line of code will run a bash shell inside Ubuntu in an interactive way. Of course, at the beginning, Ubuntu will be not available. So that's why Ubuntu will be pulled automatically, built, and then run. This is done automatically by this command. Another thing could be running a web server, Nginx, Apache, the Apache one. I mean, they could be, I mean, examples of web service. So Docker run Nginx will pull the Nginx image from the Docker repository, will build this image, and will run the Nginx. But it doesn't work. Why it doesn't work? Because, of course, the Nginx needs to expose the port. Typically, a web server is going over the port 80. That's why we have to specify that the port 80 of the guest needs to be mapped with, for instance, the port 80 of the host. So that means that then we open a browser, we go on the web page using the port 80, like localhost port 80, and that means we will open the Nginx website. This is called port forwarding. So we are forwarding a request from the port of the host to the port of the guest and vice versa. Of course, these are customizable. Okay. Typically, I mean, it's a standard that the port 80 is used in a web service, but the port we want to open in in the host could be also different. And typically is different also for a security reason, because I mean the bots online scans for port 80s, but if we use a different port, of course it's much more difficult to understand. Docker volume. Docker volume is important because I mean, of course, we need data associated with these containers. This data needs to be also detachable from the container. So that means if I have just to change the application inside the container, but not the data, I can detach the volume, modify the container, and then attaching the volume again. The volume could be done of there are two types of volumes in Docker. One is creating like a closed file where we cannot really read inside, but only Docker can do it. The other one is mounting a file system, so like a specific folder of our host inside the container. This is really a common approach because we can read, of course, the files that the Docker containers will create. And for instance, for logs, this is the most common approach. That's why we have in the container a bit mount to the file system. In the file system, we have a Docker area, And this Docker area is used like a volume by the container. And then, of course, it uses the memory for continuing. Okay, these are tutorials for working with the Docker volume. And for example, a way to add a database like a volume, I mean, the location where data are stored for a database like a volume is this. So Dagger run -d Mongo will run MongoDB. MongoDB is a database, NoSQL. It uses JSON documents in the Dutched mode, so in the background. Then we create a volume. The volume could be called like we want. My volume is an example. And then we run instead Mongo with this volume. So we map the volume we created in the host, my volume, with the path where Mongo needs to store the data. Of course, I mean, this is typically suggested by Mongo itself. Okay, so the path that we have to use is suggested by the creator of the container. So data DB is where MongoDB writes the. Then, if we want to deploy a custom web application, and then we have to specify, for instance, from where Nginx serves the file, we have to do something like this. So we have Docker run, we have the name of the container, some Nginx, we have the volume, so we specify a path in our file system, so my HT folder, for instance, into the path of the guest, so the container, so in the HTML folder of the Nginx, and in this way we run the Nginx server. Docker provides also networking facilities, so we can create a network where these containers will live. These are the commands. So Docker network creates my network. Docker network ls will show up all the networks that are created. At this point, with two containers, and then we want that these two containers works over the same network, we have to specify, for instance, for the Nginx to connect to the network, my network. Same story for MongoDB. They will be in an isolated network. So if we run other containers, they cannot see each other in terms of networking. So the Nginx cannot ping another network, another container that will be outside of the network. Okay, so this is important for, of course, managing networking and the security of these devices. As I said at the beginning, we can build our own images. This is important because typically, there are images already on the web, but typically we want to create our own image. And we do it with Dockerfile. The Dockerfile is a file where we write down instructions, and then we have to build the Dockerfile using the build command, tagging the image, so giving a name to the image, and specifying the folder of the Dockerfile. Let's consider, for instance, an application where we have a Flask web server. This is a really easy Flask web server that provides a page with the hello world. This is an example of Dockerfile. Okay, so I don't spend much time on this because it's something quite common to build. But about Docker, discussing about Docker, it's important this. So from allows to start from an image which is already present on the web. This is a Python image, specifically the version 3.8. So that means the Python community builds a container that has just Python installed and the 3.8. You can already see the powerful of this approach, because if I have to test my code and my code works in the 3.10 or the 3.11 only or the 3.9, I don't need to install Python in my system. I can just run a containers with the Python 3.8 and then run in the code. Then I move in the working dir. It creates and uses this Python Docker folder inside the container. Then I copy from the host to the guest the typically requirements txt where there are the dependencies. the run command will execute a command, so the pip3 install requirements will install the dependencies, and then typically with this copy dot dot, we just copy the entire folder of the host inside the guest. So at the end of the day, we are copying the Flask application, because then with the cmd command, which is a list of strings, we call the Python free Flask application in this way, specifying also the host. So we build the application with this command. So docker build my Flask server dot. Dot is because we are already inside, we're supposed to be inside the Docker file folder. And then we run it. For running it, we use the myFlask server, which is the image that we created. In this way, we create a container. The container is exposed over the port 5001, okay? And then it will be accessible by the application. In this way, I mean, we can also create a different front-end and back-end application. So this is, for instance, for backend, we have a route that allows to have like a JSON data, like the email of a person. Then we create the backend container, okay, and we run it. We create also the front-end backend container, and we run it. And these two images can communicate with each other. The creation and the adding of a database could be done with this few line of code. So MongoDB, you have to specify even in this case the port. This is the standard port of MongoDB, the 27,017. And then we run the Mongo database, and at that point we can use also the database to store data and retrieve data. So really, in a few line of codes, we can create a microservice architecture with all the services are decoupled but connected with the REST API, and we are immediately in the virtualization. Just let's think about containers, which is the Docker Compose, about Docker. Docker Compose, it's really useful because allows to deploy multiple containers at once. Currently, we had to run the backend, the front end, and the database in 3 different command lines. Before, we had to build the backend and the front end with different command lines. Docker Compose creates one YAML file where all the containers, I mean the images, are specified, and just with one command, which will be the Docker Compose build and the Docker Compose run, will run the entire stack of applications. A YAML file for, I mean, people that are not used to use is like a JSON, okay, as the same backend, let's say, of a JSON, so we can use it in Python also like a dictionary. But it's more user-friendly, let's say human-readable, because we remove the brackets. We have still a key-value approach. We have still the possibility to create a list. So this is a key, for instance, calling beards, and then we have the name of the beards. So we have the values. Or, I mean, we have that a key collects another dictionary. It's exactly like this. So do, and then we have other key values. So the Docker Compose, it's something like this. So this is Docker Compose with 2 services. We have one web service that builds over the Docker file, which is still on the current path, which is called with dot. We expose the ports 8000 over the 5000. The volumes that are used, one for logs, one for the code. And then this is linked with another image, which is called Redis. And the Redis is a in-memory database. And this is a second service that could be run. And then we specify the volumes, okay, like the log volumes. This is another example, services, MongoDB, to run the MongoDB database. Restart always means that even if there is a crash, the container will restart all the time. We specify environments like username and password, and Mongo Express. Mongo Express is the user interface software to read data inside Mongo. So typically Mongo comes up with these two containers. And then we can specify same root and example, so same username and password, and the URL from which we can use the Mongo Express. With Mongo Compose, then we can start, stop, rebuild service, reading the status of the running service, streaming the log output of the running service, run a one-off command on a service, and this is how can we install it. So install Docker Compose plugin. And then, I mean, it's possible, of course, to build exactly the same application we did before. So front end, backend, and database using, of course, Docker. We will see more about Docker Compose and YAML file, I mean, in practice in the afternoon session from Sarah. So about introduction of containers, this is all. So if you have any questions, we are quite in time, but in the break. I don't know if there is time for some questions, Professor Peters.
Okay, I have a bit of a specific question about Docker.
Yeah.
Okay. In the examples of that have been made here today, and in general, in the ones I've seen online, I see that Docker is used with like images. When you have like an operating system image on it, usually it's Linux. But I have an application and I would need to mount a Windows image on Docker. And I was wondering if you need like hypervisor technology to do that, because like I was reading some Windows docs and they say that you need to activate Hyper-V on Windows to do that.
No, the point is this one. You can virtualize Windows and you can virtualize also Mac OS. Clearly, you can virtualize Mac OS only on Mac hardware, no? Because of the limitations Mac OS has. And you can virtualize Windows, let's say, almost everywhere, except the fact that Windows needs some BIOS, of course, properties activated. The point is that typically the containers creator prefer to use some Linux system because anyway, Microsoft needs a license. So it's not so lightweight to be virtualized because it's an operative system which is quite complex. No, used mostly for desktop application, even if there is the Microsoft service, of course. So that's why typically the containers providers, I mean, prefers to maintain a Linux system. There are also containers that are with the really teeny Linux systems, which is called Alpine, because Alpine is an operating system which is big like some megabyte. And this is done to really create microservices that are really small. And why we need something small? Because microservice and containers are there for being migrated.
Yeah.
So the big advantage is that we have to migrate them. And if we need so much time to migrate it from a machine to another machine, then of course we are not in the cloud paradigm.
Well, I'm asking this question because I'm trying to distribute an application in a way that might be a bit unorthodox. And I'm not sure whether it's actually feasible because I would need to, well, besides having a Windows image, I also would need to install a few things that need GPU access on a Windows image in Docker. And I'm trying to understand whether it's feasible or whether I should distribute this app in another way. Because I've actually done, I've done the standard thing, the web application on Linux, server client. I've already done that once, and that's pretty easy on Docker. It's like the standard use of Docker, and it's not hard to do that. But I think I'm trying to understand whether it's feasible to do what I'm talking to you about, and I don't think it is, but if it is, I'd like to try it.
Well, you can also use a hybrid approach, let's say.
Hello? I can't hear you.
It's frozen for some
Yeah, I think.
I think he said to use a hybrid approach, but I'm not quite sure. He's going to come back.
Oh, there he is.
Yeah, I said, I mean, using an hybrid approach like a virtual machine, and inside the virtual machine, one or more containers. Because with the virtual machine, you are, I mean, it's easier probably to use also the GPU, to use some specific resources. And this virtual machine could be easily a Windows server. With a container, I mean, it's something that I don't typically see, really. I mean, it's doable, but it's something that is not common. But I mean, on other VirtualBox, I virtualized Windows machine many times. I mean, it's not an issue.
Okay.
Except the fact still that you need a license for full use.
Yeah, I mean it's a pretty complex it's a fairly complex application that is
But maybe that's why you need to decoupling it. So put a virtualization approach, traditional one,
yeah.
so virtual machine, and inside the virtual machine you install the Docker engine, and the Docker engine helps you to run one or more containers.
Okay.
And this application in the container could be also some Linux system, for instance. Or if you can, it's just Windows, you install it directly in the virtual machine.
Oh yeah, I mean probably with the probably what I'm doing maybe yeah. I mean probably the virtual machine is just better overall. Just have a make one virtual machine and just you know just give that
Yeah,
around to people who need it.
you could do it. I mean, virtual machine is still here, are still here to be used. I mean, even if the world is moving to containers, I mean, there are still cases where virtual machine are
Yeah,
important
maybe
or are the best solution.
maybe it's probably better in this case because this is like this is not probably a microservice, So yeah.
Exactly. From what I understand, it's not a microservice. That's why it's
Yeah.
Are
probably
there
the
any other
component.
questions?
Thank you.
You're welcome.
Are there any other questions?
Yes, I would like to ask Lorenzo, what is the benefit of using Docker compared to making, for example, executable files or sharing the code? What I mean is, as a developer, what do I get out of Docker that I couldn't get by sharing my code with my partners or making an executable file and sharing that?
Well, first of all, portability. Platform is called platforms, the dependencies. If you share your code, you need to share, let's think Python code. You need to share your dependencies. So that means you need to share your requirements file. Then the other person will need to install the requirement files inside a virtual environment, probably. Otherwise, it makes a mess in the system, and then running the application. The Docker container it does this for you. You have just to send the image of the Docker container. Inside the container, you have already all the dependencies that are automatically managed. And so, I mean, the portability of the application is at the maximum level at that moment. So I can have an application that can run in also different operating system, different version of operating system. In a computer where maybe I have the Python 3.11, but my application needs the Python 3.10. I had this issue a couple of days ago using an encryption library. This encryption library was available only for Python 3.10, but I had already the 3.12 in my system, so I couldn't use them. I had just to install again Python, the 3.10, but I don't want to mess up with my operating system. So at that point, I can put it inside my Docker container. So portability is for sure the most important thing in the example